subset which is the set of non-elementary representation, elementary representation, which consists of the representations with values in either the affine group or the group of SU2, which preserve a metric on the sphere. And you have an open set of representation which are dense. We have seen that. This open set can be shown easily from the techniques we have seen that it is in fact dense in the bifurcation locus, namely that you can always perturb a given representation in the bifurcation locus into a representation which has dense image. And you have a certain family of complicated sets. So these sets are algebraic subvarieties, but the whole family of these algebraic subvarieties can be really complicated set, consisting of the representation that are not injective, which we call the special subvarieties. And these special subvarieties can be points if the representations are rigid, or varieties of any dimension. But these family of sets are going to the union of all these special subvarieties are going to be dense in the bifurcation locus. Okay, this was exactly this is due to the theorem of Sullivan that we state at the end of the last lecture and that we almost sketched.
Those varieties are?
So these varieties, the special subvarieties, so given a finitely generated marked group with R generators, G, so this is a marked group. So with R generators. So let's.
Sorry, can you change the source because you cannot see? Can you change the color?
Oh yeah, you don't see? Okay. Sorry. So I will. So you take. We take a marked group with R generators, G1, GR, and I will continue in white. And you look at the set that we denoted by lambda of G. So this is the special subvariety associated to G, which is a set of R tuples of matrices such that any relation satisfied by the GIs in G are also satisfied by these matrices. By the GIs is also satisfied by the matrices AIs. So more precisely, if you take a word in the G1, GR, which is equal to the identity in G, then if you substitute AI to GI in this word, it is also the identity in PSL2C. So the first result I want to state, I will not prove that result. It's a quantitative statement. It's the same. So it is a statement which says, as well as the Sullivan theorem, stability theorem, that the union of all the special subvarieties is dense. But this statement, which has been obtained by Glutiuk, is a quantitative version of that theorem. So here is a theorem by Glutiuk. And it tells you how much these special subvarieties fill the bifurcation locus with a quantitative estimate. And in fact, this theorem is true for any Lie group. But I will state it in the case of PSL2C. I have not verified. This is not every Lie group, but I think non-solvable is important because you need to have 3 subgroups inside. So, of course. So, so let K be a compact set in the bifurcation locus. Sorry, this is not exactly, this is not precise. No, this is not it. Sorry, it is in, sorry. So this is a compact subset of lambda of the free group, so of the set of representation of the free groups, consisting of non-discrete representation. Then there exists a constant, C, positive constant, such that for every A in the compact set, and for every integer L sufficiently large, there is a representation. So I think of A as being an R tuple. Okay? So there is another R tuple which is close to A. In the sense that the distance between this new representation and the initial representation is bounded by this estimate, where kappa is a fixed number. I think it is. Yes, it is a number which is between 0 and 1. And the precise value is that one. Okay? And such that A prime has a relation in the entries of length less than the integer L. Non-trivial relation of length less than L. So you can find close to a given representation of your compact set another representation which is no more free. So there is a non-trivial relation, and more or less you can estimate the length of this new relation. So this is a quantitative version of the theorem by Sullivan that we have. So this is really nice. And in fact, this is a theorem which extends the Sullivan's instability theorem to more general Lie groups. And there is no other proof than the proof by Glutzuk. So this is so the theorem of Alexei Glutzuk says that if you take any point which is in the bifurcation locus, more precisely with a non-discrete image, then you can approximate that point by points which lies in some special subvarieties which are of controlled complexity. Okay, where the complexity is defined by this statement. But you can also try to do the thing in the opposite way. And this is rather interesting. So I will try to present for you some results which I don't consider as really definitive. I suppose that we can do better, but it's difficult. So the idea, I recall you that if you take a real number, alpha, we will try to speak about approximation of real numbers by rational numbers, and then we will try to mimic what we do on R in the context of non-discrete representation, meaning that we will try to look at how we can approximate a given representation by representation in special subvarieties. So if you take a real number alpha, we say that it is, so in fact, many of the real numbers alpha are badly approximated by rational numbers. This is called the Diophantine properties. And a Diophantine number, by definition, is a number such that if you make the difference between that number and a rational number, then it's going to be bigger than some constant over q power 2 plus epsilon. So for any epsilon, positive number, there is a constant such that this is true for any rational number p over q. Yes, sorry, that's right. For some epsilon, there exists a constant such that this is true for any rational number. So this is called Diophantine number. Okay. So, and the result, which is really classical and easy to prove, is that almost every number with respect to the Lebesgue measure is Diophantine. Namely, it is badly approximated by rational numbers. So here is a theorem which goes in that direction, and as I told you, I'm not considering that this is a So in fact, it is also true if you replace the free group by any group. But we will do that for the free group. So, for almost every A, a representation of the free group, there exists a constant such that if L is large enough, so L is again an integer, and A prime is again a representation of the free group that has a relation of length L, then in fact the distance between A and A prime is bounded from below by some quantities. And the bound is the following. Let's write So let's write the bounds here. A prime minus A is bounded by, is bounded from below by exponential minus C times L squared. So it's really bad. I mean, it's a sequence which tends really, really fast to zero, but still it is an estimate. So it's a result which goes in the direction that almost every representation is Diophantine. But so what we would like to have is something like an exponential here. So if you think, I mean, it would be nice. And in fact, to have so these kind of questions are, in the case of representation in the group SU2, can have the same kind of question. It is really interesting. And these kind of questions have been studied quite a lot by Bourguin and Sarnak and Gamburd, and they propose a kind of conjecture that I will discuss later, and which is really related to that. So,
can you specify having a relation of length R, L?
So that means that there exists a word in the free group of length L, such that if you substitute the AI, I mean the letters to the AIs, or I'm not sure that I said in the good, then the relation, the word is going to be identity.
Why do you never use the word kernel?
I don't know.
There is a word of like S in the kernel.
Right. That's right. Yes, this is exactly that. So, in fact,
Can you repeat the question again?
No, it was not a question.
No, remark.
Frequently he's trying to go around the concept of kernel homomorphism.
you're right. You're right. So let's try to explain how we can. In fact, this is really not a deep result, and this is just to. But I will. So first of all, these kind of questions of bad approximation by representations having relations is related to the following question. If you take a representation, A, you can, so suppose that it is injective. There is no relation between the entries of this representation. And I have not said that, but it is generic in the sense that if you, outside a certain countable union of algebraic submanifolds, a representation is injective. Okay? Because for every word, the fact that this word is going to be identity, so this word is in the kernel, defines a subvariety which is of strictly positive codimension because there exists an injective representation, for instance, the Schottky group that we heard about yesterday, I think. And so take such a representation. I mean, it is not necessary. Think that this is such a representation. Now you can ask, take all, so suppose it is dense. Take the ball of radius r in the free group and look at all the images of the elements. Because it is dense, some of these elements, when the ball is large, is going to be really close to the identity. And we want to measure how close is it. So let us introduce the following number. dl is equal to the infimum, so to the minimum of the distance between omega of A and the identity, where omega is a word of length bounded by L. And it is not trivial. Okay. So of course, if the representation is injective, these numbers will be positive. But if it is dense or non-discrete, this number tends to 0 while L tends to infinity. Okay? And in fact, it is easy to prove that if you cannot, I mean, if a word of length L is going to be far from the identity, any word of length L is quite far from the identity. Let's say we have an exponential bound from below. Then, if by perturbation of your representation, you cannot make this word going to be identity, if you will have to move a lot. Okay, this is the idea. So, of course, if you bound from below this number, let's say, for instance, by an exponential sequence, you will have an exponential bound from there. Or if you bound that number by this estimate, you will also have this estimate for that here. Okay, so in fact, the question is to bound this number from below for a generic Lebesgue generic representation. And in fact, the proof that we will give or sketch will use some estimates on the sub-level subsets of P Paris-sud harmonic function. I will explain why such estimates can give this kind of results. And in the course of the proofs, we will see that this is interesting to see that we will use the fact, so we will get a result on non-discrete representation by using the fact that in our family there is a discrete one. So we will use discrete representation to prove a statement about non-discrete one. And in fact, this is a phenomenon that is quite common in this kind of, in this topic. So, let us introduce the family of functions for every word, omega. Let us consider the following function. So we take the log of the distance between omega of A and the identity. Okay? Of course, if omega of A is close to the identity, because this function, so this function has a logarithmic pole at any matrix for which omega of A is equal to the identity. Okay, so if you have a matrix for a representation for which omega of A is close to the identity, this function is going to be really negative. Sorry? So in omega, omega is a word. Omega is a word in the generators of the free group. And A is a R tuple. And omega of A means that you substitute the matrix to the okay? So you consider this function. So it will be really negative at a repeat.
A de oméga.
Sorry?
On pourrait facilement l'écrire A de oméga.
Ouais.
A, c'est la fonction. Et oméga, c'est le nom.
Right. Okay. Right. Okay. But I will denote it like this because I think either I will. And you divide this function by the length of omega. The length of omega is the number of generators that you have used to write your word as a reduced word. Okay? So you consider that function. So this function has the property that, in fact, if you take any compact set of A, so on a compact set, these family of functions are going to be bounded from above by some constants, because the norm of a matrix, so you multiply the length of omega matrices, okay, which are bounded. So okay, and then you take the log and you divide by the length, so you will have a bound from above. Of course, it's not going to be bounded from below because, as we said, if this word is close to the identity, the function is really negative. So we have this. On the other hand, this function, as I said, so we would use pluri-subharmonic function. This function is pluri-subharmonic. Okay, if you take, so it is not true for any norms, but for instance, if you take the L2 norms in matrices, then this will be true. Okay? And so you have a pluri-subharmonic function, which is bounded from above. And you know also that if you take A to be a Schottky representation, at such a representation, this function is not going to be too negative. Because a Schottky representation, the image of a word of length length L, is approximately an exponential of L. Okay, because it is discrete. This has to be proved. I will not do that, but it's not so difficult to prove that in the Schottky group, if you take a word of length L, the corresponding matrix is going to be of norm exponential L. So, of course, what we want to say is that...
That is for every word.
Yes, we take for every word. We want to say that for every word of length L, the set of elements A for which this function is too negative, which would correspond to the fact that the associated, the image of that word is going to be close to the identity, is small. And then we will use Borel-Cantelli to say that, in fact, for almost every word, we have the estimates that we want. Okay? So we really have to prove that for some pluri-subharmonic functions, the sublevel subset, namely the set of elements where the function is bounded from above by some constant, is small. And this is something which is available. There is I don't know how to call this is a theorem, let's say, by, I don't know exactly who, I read that in Hermander, but I don't know if it is a Hermander, okay, who proved this kind of estimates. So let's, I will state the estimates and then I will just, so it is based, so we will take, so let B be a complex manifold. K, this will be a compact set in B. And P, a point in B. Okay, then let's U from B to R, a pluri-subharmonic function. Which is bounded from above on B by some constant. So psi is bounded from above by some constant that we will call B. Sorry? And, U. And U of the point P is bigger than some other constants. Let's call these constants A. Okay? Then, so I will do again the conclusion here. I will write again the conclusion here. Then, the integral of the exponential of, so I forgot to say that there exists a certain constant associated to, which depends on b, k, and the point p, okay, and on the constants b and a, such that the integral on k with respect to some volume forms on b that you fix, v is a volume form on b, which will be fixed dv. So this is bounded by a constant, another constant d. So I should say exactly what are the quantifiers in that situation. So the quantifier are like this. You take b, k, p, and the constants a and b, and it says that there exists a positive constant c and a constant d, such that this is true if you have the following inequalities. And you see what is important here is that you can have a logarithmic pole at some point, but then you do exponential of minus u. So if there is a really negative logarithmic pole, this quantity is going to be really positive. So it will be impossible by the fact that you have some bounds. Okay? So this is the way that you can control the volume of the set of points where a subharmonic function is bounded from above by a constant. Okay? I will not go further. This is just the idea. Then it's just a question of writing the things. So this is the idea. So, and I should say that. I should say that, in fact, the theorem that we proved about, so we proved that for almost every representation, this sequence DL is bounded from below by some sequence, exponential minus L squared times the constant. And this is an estimate that is due to Kaloshin and Rodniansky in the case where the representation is in value in SU2, but in fact their proof is follows almost the same ideas. They don't really use Paris subharmonic functions, but they arrive at analogous estimates by other methods. And but in fact, their proof generalized. I mean, this estimate generalized to representation in PSL2C, and I suppose for any Lie group. So let me just tell you what is the conjecture by Gambourg, Sarnak, I forgot the third. I said you a few minutes ago. It's going to come back to my mind. Bourgain. So Bourgain. Thank you, Etienne. So the conjecture is a conjecture about representation in SU2, and it says the following. For almost every A in of the representation of the free group in SU2, there exists a constant positive such that for L large enough, DL with the same definition is bounded from below by exponential minus Cn. So namely, we have really an exponential estimate. And there are also related conjecture to that, but I don't want to, really on the dynamics of this representation on SU2, but I don't want to enter into this. But this is related to some dynamical properties of individual representations. So this is really interesting too. And I mean, it's harder to prove that for SU2 than to SL2C, so we could try to also think about that. So it is really possible that we have this kind of estimate. Okay.
So in the opposite direction, in the easiest direction, are you able to construct new group representations?
I tried, but I don't know.
That looks easier.
Yes.
But it is not.
I have not thought a lot, but I tried last week and I didn't. I don't know. But maybe it is easy. Okay, so that was. So I will change a little bit the topic. So we describe some Diophantine property of representations. Now I am going to speak about what I announced at the beginning. That is that for some for some particular families of representation, of special varieties, so sequence of special varieties, we will see that these, which are canonically defined, we will see an equidistribution phenomenon, namely that the special subvariety is going to become more and more complicated and is going to distribute itself in the whole bifurcation locus. And so, beginning from now, what I am going to speak about is a common work with Romain Dujardin. And in fact, also the proof that about the Ronionsky-Kaloshin estimate was also obtained discussing with Romain. So here is what we are going to try to do. Take a word of a really large word in the free group. Okay? And consider the representations for which this word is mapped to the identity. It's better, I think, no? So, okay? So this is a special subvariety. This is just the special subvariety corresponding to the group with R generators where this word is a unique relation. Okay? So if omega is a word, let us define lambda of omega. This is a special subvariety which is defined as a set of representation such that omega of A is equal to the identity. Okay? And what we would like to prove is that if this word is a word taken at random in the words of as a word of really large length, then in fact this subvariety, this special variety, is going to fill almost all the bifurcation locus, and more or less it's going to equidistribute in the sense of currents, to a certain currents that we will describe. So for this, as I said, we will use, for produce these words, we will use a random walk on the free group. And in fact, what we will be able to prove is not exactly the statement I said, but is the following statement. Take a random walk on the free group and take a random composition of large length. Then we will consider not the special subvariety of this word, but of a power of this word. For instance, the square of that word. We will be able to prove that, but not for the. We don't know for a word. Let me state the theorem. So we have to take a random walk on the free group. So as Christian said, to define a random walk on a group, we have to specify a measure which will be the distribution which enables us to take at random an element. And then we take at random an element with distribution this measure, and another one independently, and another one, etc. And then we take the product of all these words that we have taken. So again, I write for the free group, but it can be any finitely generated group. But to clarify the idea, we will take the free group. And we will suppose, for simplicity, so as in Christian's talk, we have to impose some moment conditions, but we will be simple. We just take the following measure. We take the set of generators, the set of their inverses, and we take the equidistribution measure on that. So namely, we take at random a generator or an inverse, and we make the composition. Okay, for instance, we think of that. So what is important is that of finite support, or with a moment assumption. But let's think about the measure on the equidistribution on the generators and their inverse. So the theorem is the following. So let P be an integer. I mean that the measure, so this is a measure on the free group.
So the measure you just described has totals.
Repeat again? I have not.
What do you mean by that?
I mean that the measure of an element is 0 apart from a finite set of elements.
Okay,
So what?
I did not understand what the measure you described was.
So you take,
I thought
in the free group?
were like independent coordinates or whatever.
No. You take the generators, so there are generators, you take their inverses, and you take the measure which assigns to each of these elements in this family the probability 1/2R. Okay? So you take an integer, P, then so to pick at random a sequence of elements is the same as taking a sequence of elements in the group G, which is generic with the Bernoulli measure mu to the n. Every sequence. So you take a sequence. And generally we will denote this by G. So you take a random sequence of elements, and then the claim is the following. So just a notation. If you have a random walk, so we will consider some product like this, okay, where the GIs are taken randomly. And this we will write as the right product. So we multiply at each time by the right, and it's going to be written like that. This is the right product. Okay? So you take this word, you take that word to the power p, and this is going to equidistribute in the sense of currents towards a current which depends on mu but does not depend on p. We'll see that. Sorry? No. Thank you. So that was. So of course we would like to have p equal 1, but we don't know that. So this is a current. So that statement is an equidistribution statement, but it is not really deep, in fact, that statement. I mean, according to what we know about random products of matrices, and according to some deep result in this theory. So this equidistribution result, in fact, relies on a potential theory. This is a 1-1 current. So this is a current of integration on some manifolds which are of codimension 1.
Why are they codimension 1?
We will see that.
So that's part of the theory.
Yes. In fact, this is the first time I will reformulate the theorem, and we will see how it goes. In fact, this is the first time I state that theorem in that way, and in fact, it is possibly true, not for that one, but for a irreducible component of that one. We will see. Maybe there is a mistake in the formulation here. We will see. I will reformulate and we will discuss that. But what I want to say before we...
Naively speaking, lambda omega has codimension 3.
No. I will explain to you. No, because this is a word to the power 2. So how do you detect that a word will be of order 2? You take its trace. I mean, this is... so either it is identity, that word, or it is a square of the identity, namely, this is a rotation. And to see that an element of PSL2 is a rotation of angle P, you just read that on the trace, which is a codimension 1 condition. So that's the reason for these powers. But in fact, so these powers, if you take a word at random, and then you take its power, it is not at all a word at random. Okay, so of course, if we have p equal 1, it's much stronger. It would be really stronger. So I come back to what I was saying, is that, in fact, so how do we prove this theorem? So to prove a theorem like this, we use potential theory. Namely, if you want to prove that a sequence of currents converge to a current, you can try to prove that the potentials of these currents converge to something. And so this is the first tool. And the second one is some results, as I said, which are deep results in the theory of random matrices. But this is not really Okay, what is the deep result is the fact that this current, actually, its support is the whole bifurcation locus. Okay? So that namely because, for instance, this sequence of varieties, they equidistribute to a current, okay? But these currents could be somewhere here. Okay? But what the theorem says is that the support of T, which is usually called T BIF, okay? Because it is a current which is a quantitative measure of the bifurcations, in the sense given by this, because of course these are special severities, so they say that you have bifurcations. Okay.
But you said that limit current depends on mu?
Yes, and this at all.
Not P.
And not P. So I will finish here. So end. So this is the important part, and the support of TBIF, of the bifurcation current, is the bifurcation locus. So let me just explain more. So reformulate that theorem in a theorem concerning trace of elements of this. So in fact, we are in PSL2C, so trace is not well defined, but what is well defined is the square of the trace. So you take that. Okay, and you want that this is equal to T. So consider that this is a codimension 1 submanifold of the set of representations, because this is a holomorphic condition in A, okay, which depends on a random word of length n, okay. And so, what the reformulation says is that this tends, as n tends to infinity, to a certain current, TBIF, which depends on mu, but not on T. And if you... Yes, sorry, yes, thank you. You take 1/2n, sorry. Of course, the volume of this is going to increase a lot, because you see that this is an algebraic equation whose degrees is approximately of linear, this is linear in n. So the volume of that variety is going to increase linearly, so you have to divide in order to hope for an equidistribution result. So I just finished to say that if you take a matrix and you suppose,
So can I ask again the same question? Why is it clear that this is a codimension 1 submanifold?
so, okay.
One equation or the general equation?
No, because the representation, sorry, it's connected, okay? It's connected? Okay. So you can read, for instance, you can read on the trace if an element of PSL2C is of order P. Namely, an element of order P is a rotation, which can be written yes. And so you compute the trace, it's a cosinus 2 times the cosinus of 2p over p. So if you take t is equal to 4, then you obtain that statement. But as you see, in fact, this is a wrong statement. Namely, this could be bigger. So in fact, this is maybe finite union of irreducible components on that one. In fact, I'm sorry, there is a mistake here, but up to some union of irreducible components, it's true. So I'm sorry, this theorem is not true, in fact. So it's not true, but the idea is that you have some such statements like this. You have some special subvarieties associated to this relation which converges. Okay, so I'm going to stop. I will do the proof of that theorem in the next lecture.